Hello, and welcome back, everybody, to the second talk for the day, session 2 of on-chain scaling. I hope everybody might know our next speaker. His name is Chronos Crypto. Well, at least that's what he goes by. His topic will be Xtreme Thinblocks, which those of you listening may know that it is one of the alternatives to the other proposed compact blocks proposal that core devs have coming up with. So this is going to be an interesting talk. It has been alluded to several times in the past and earlier yesterday as well. A little bit about Chronos Crypto. He is a longtime Bitcoin enthusiast with a degree in computer science and a passion for finance and macroeconomics. His perspective on the world financial system is that another catastrophe is increasingly inevitable, although incredibly, I suppose that also works. And Bitcoin needs to be ready for it. Over the past 2 years, he has operated a crypto-oriented YouTube channel where he covers the finer points of blockchain technology. So without further ado, I'm going to hand it over to Chronos Crypto.
Thank you, Jerry, for the introduction. My name is Chronos. You might not believe it, but it really is true. My parents didn't name me Chronos, though. I named myself Chronos, which is dangerous, I have to admit, because when people name themselves online, usually they pick something like Zergrush99. So I'm lucky that at least it's somewhat not embarrassing. Chronos, as you may know, means time. It's Latin. And I think I'm actually named after Bitcoin because if you think about it, time is money. And soon you will realize that Bitcoin is money. Therefore, Chronos is time, is Bitcoin. Totally makes sense to me. Maybe. So like many of you, I'm interested in the halving that's coming up. So I thought I'd give you some tidbits or trivia about the Bitcoin halving because it's like a week or a week and a half from now. And it only comes every 4 years. So it's a bit of a celebration for Bitcoiners, as you know. So I was looking at the halving table. Like every 4 years, the Bitcoin output is cut in half. So here's the question for you. If the output were not cut in half, if it just stayed at 25, currently it's 25 Bitcoins per block, at what point would we hit 21 million Bitcoins? How long would it take? As you know, the end of the Bitcoin emission cycle is the year 2140. It's when after all of us are dead. I can actually see you guys, even though you feel like you're all in your own little rooms, completely silent, like you're in a jail cell. Don't worry, I'm the jail warden. I can see all of the attendees. So if you chat, I can see you. So I want to see your answers on when you think 21 million Bitcoins would be mined if we did not cut the block reward next week, if we just stayed at 25 Bitcoins. Give you a moment to think about that. No fair using a calculator. There's an interesting thing about the Bitcoin block reward being cut in half every time. It follows an exponentially decreasing curve, and it's similar to, here's an analogy. Imagine a frog jumping toward a wall, and with each jump, it jumps halfway to the wall. The question is, when does it reach the wall? Well, with each jump, it gets halfway closer, but it never gets all the way closer. So you could say that's an infinite frog. That is actually the same as the Bitcoin emission cycle. Every 4 years, we've jumped halfway again to 21 million Bitcoins. So actually, it would take exactly 4 more years, give or take, because sometimes blocks come out a little bit erratically, to travel the other halfway. So after the first halving, we had traveled halfway to 21, which was 10.5 million, and this is the second halving when we're traveling halfway again. So you can think of it as halfway each time, and that's a good way to see, kind of get your mind wrapped around that curve. Another really interesting thing about that curve is the way it tapers off at the end. Here's another question for you. How long do you think it will take to mine the very last Bitcoin, that 21 millionth Bitcoin? And I'll give you a hint, it's a quantity of years, which is pretty amazing because in 10 minutes we can mine multiple Bitcoins, but in the year 2140, we're mining just tiny amounts. In fact, the block reward will hit 1 Satoshi, assuming that the social consensus is maintained. So that's the question. How many years will it take to mine the final Bitcoin? The answer is 36 years. I mean, you should be glad you're in the mining business now, because if it takes you 36 years to mine 1 Bitcoin, that's going to be, these are like the good old days of Bitcoin mining, when you can actually mine whole Bitcoins. And that really just emphasizes how much of the emission cycle is coming at the front end right now. So Bitcoin is definitely inflating quickly relative to the future right now, and that's one of the reasons that, in my opinion, we don't need the fee market that we're starting to see where people are paying high fees to support the network, because Bitcoins will be coming out quickly for the next 10, 20, I would say 20 years, maybe 30 years before you actually say, oh no, now we really need fees to incentivize miners to secure the network. So enough trivia, let's get to the talk at hand. We're talking about Xtreme Thinblocks. It's quite an honor for me to be able to present on Xtreme Thinblocks, because it's been the culmination of a lot of effort of a lot of different people, and I actually wasn't involved. I didn't code Xtreme Thinblocks at all. I showed up after the fact. I was like, wow, this is cool. I should talk about it. And I was invited to speak at this conference. So thank you very much for the opportunity to present on Xtreme Thinblocks, because there's a lot of people who have put a lot of work into it, and I feel like it's their right to give this presentation, and they've handed that over to me, so I'm very thankful for that. So let's get started. Let's take a look at the agenda. Today, first we're going to go in depth on how Xtreme Thinblocks works, and so this is the Bloom filters that it uses. We're actually going to cover how Bloom filters work, and then we'll look at some live network data. This has been collected, and there's actually a talk around how the data was collected later today. Andrea will be talking about that. So we're going to look at the data that was collected on how Xtreme Thinblocks compares to the standard block propagation that's used in Bitcoin today. Then we'll look at the impact on scaling, that what fundamental difference can it make for the network, because it's nice to propagate blocks more quickly, but it's nice to know what that can mean for the network. And lastly, we'll talk about how you can get involved. So let's get started. Unfortunately, this is a PDF presentation. It's not PowerPoint, so I can't make the slides appear over time. You see the whole slide right now. So it's your job right now to ignore this beautiful diagram at the bottom. Can you see my laser pointer? This is me saying, ignore this beautiful thing. I know it really, really stimulates your mind, because the zeros and ones are perfect for your left brain, and the beautiful colors are perfect for your right brain. So I know you just want to focus on that. But let's start at the top. Talk about Bitcoin nodes. As you know, Bitcoin is made up of nodes. There's no such thing as, by the way, the Bitcoin mempool, which is the memory pool of all transactions waiting to get into a block. People say, oh, the mempool is growing or it's full. Well, it's not. There's no such thing as the Bitcoin mempool, because each Bitcoin node has its own memory pool, and each node keeps its own list of unconfirmed transactions in its memory. This is important because if you run a node with not very much memory, you can still do that. You just shrink your mempool by saying only transactions with a high enough fee to get in will be stored here, and your memory pool is smaller. All of you track the mempool by using different services around the internet that show their Bitcoin memory pool, but that can be a little bit off. I often see like a 12 megabyte mempool, which means 12 full blocks worth, but then you see that the last block that was mined wasn't even full. Well, that's because a lot of those transactions aren't of interest to miners. They're spam, and miners have been able to tell that. Yes, I'm saying that transactions can be spam, and so that can be a little bit misleading to say that this memory pool is this big, but another one could be a different size. So anyway, how the network works is when a new block is mined, transactions are moved from the memory pool into the block. The miner that mines the block puts them there, and then that block has to be sent around to the other nodes on the network. And Thinblocks is a way to send that block efficiently between the nodes on the network. Xtreme Thinblocks takes that a step further and uses a Bloom filter to reduce the round trips that are necessary to send blocks using Thinblocks. Now, Thinblocks was never actually put into production. It was an idea that was put forward by Mike Hearn, but it was a good idea, and Xtreme Thinblocks builds on it. So this diagram is a Bloom filter, but I don't want to tell you how it works just yet, because I want to jump to the next slide, which has a diagram of this interchange between nodes. So this is a beautiful diagram. Hopefully you guys can read it. The first horizontal line is node A, and the second horizontal line is node B. Just look at this top half for now, because the second half is the Xfin block, so it's the same thing twice. And then time is moving from left to right. So a block arrives at node A. This is a single node on the network. First, it verifies that block. This is the verification time from left to right. Time is passing. This is very, very important. If you don't verify the block first, then an attacker could send you a fake block that doesn't have proper proof of work, that they didn't even mine it, they just made it up and sent it to you. And if you don't verify it, if you send it out to the network first, then everybody else is going to do the same thing, and you'll totally bog down the network with that fake block. And so each node needs to kind of be a gatekeeper to the network and say that's not valid and to throw it out. After the verification, then you can tell the other nodes, yes, I have a real block, and that's this INV. A couple other the presentations have been talking about what this INV is. It stands for inventory. It just says, hey, look, I have a new block. Would you like it? The new node says yes. So it says get data. So these are messages between the nodes. This is INV saying, I have a message for you. Yes, please send me the block. And then here's the block in its uncompressed format. Uncompressed is the opposite of Xtreme Thinblock format. So let's take a look at diagram 2, the Xtreme Thinblock method. Get data includes a Bloom filter, which is a way of saying I have these transactions already in my memory pool. So the old transmission format was for the first node who has the block to send the entire block again, which is quite redundant because the transactions that are in there could already be in the memory pool of the second block. So the second node says, I have these transactions, and then the first node is able to say, oh, well, since you have those, I don't need to send those full transactions back to you. So let's dive into what this Bloom filter is. Very cool. You can learn more about Bloom filters on Wikipedia, but let's jump back to the previous slide and take a look at this Bloom filter diagram. So this is a super tiny Bloom filter. It's like 15 cells, but an actual Bloom filter would be much larger. I'm not going to say because I'll be wrong. So if node B, the one receiving the block, said, here's all my transactions, and listed out all of the transactions and sent those, that would be a lot of data. It would, in fact, it would not save any bandwidth or time at all because the first node could just send them again instead of just receiving them again. It's the same amount being sent over. So the Bloom filter is a way to compress that information and send it in a way that's reliable, not completely reliable, but it gets good compression instead. So in this diagram, node B is saying, I have these 3 transactions, X, Y, and Z, and each one is represented by a color here. So these transactions are going to be added to the Bloom table and the Bloom filter. And Bloom filters are just a fabulous way to store this information in a reliable way. Here's how they work. Each transaction is hashed, and hashing basically means like slicing it up and looking inside to, okay, that's not what hashing means. Hashing means giving a unique output based on the input. One way. It can't be reverse engineered. If you don't know what hashing is, you should look that one up too, because I'm just going to assume you know what hashing is. I'm not going to fool myself any longer. So it's hashed multiple times using different hashing functions, and these blue arrows represent the different hashing functions. So when transaction X is hashed, it comes out to this slot in the Bloom filter, and this is a Boolean array, basically. It either has 1s or 0s. So it says, since I have this transaction, I'm putting a 1 right here, which indicates I do have transaction X. And that's over here on the left. And then the second hashing function, which gives a different output, comes over here to this slot. And the third hashing function comes over here. So these 3 slots are marked 1 because that represents that transaction X is stored inside node, I got confused, one of the nodes memory pool, the one that's built in the Bloom filter. It's node B, but that doesn't matter so much. We're just focusing on the filter right now. So what we're doing is building this giant array, this tape of 1s and 0s, and the 1s represent, yes, I have that transaction. But there's no specific slot for a specific transaction. It's just a random smattering of different hash functions that's filling that out. And that turns out to be very efficient because you don't have to have a slot for every different kind of transaction. That would be much too large. Instead, you just have an estimation based on these hash functions. So let's take a look at Y. Y has a red arrow to here, and to here. And you can see all the slots that have arrows pointed at them have 1s in them. These are being marked 1, which is true, meaning I do have that transaction. And then the purple one, which is Z, is hashed to this slot. And it looks like just 2. Oh, no, here it is. Of course, it's 3 because you use the same number of hashing functions for each input. So interesting thing about this array is that you can see some slots have multiple arrows pointing in. If you come to a cell that already is marked true, you simply leave it as true. And this is where the information gets a little fuzzy because you don't know, does this 1 represent transaction Y or transaction X? I guess X or Z because it's blue or purple. Which of those does it represent? The receiving node doesn't know for sure, but it probably could figure it out because there's multiple hashing functions. This is just a genius way to transmit information. And the same with the cell over here between the red and the purple. You don't know if it's the red transaction or the purple transaction. So let's go back to the node communication diagram. Here's node B assembling this Bloom filter and sending it across to node A. Now node A is ready to build a new block to send it across, saying, okay, here's the new block I received, I'm sending it to you. Normally it would need to put all the transactions in the block, which would make it large, usually 1 megabyte, because that's the maximum block size at the time of this conference. Hopefully that will be going up soon. I consider it to be a bit too small. So with the Bloom filter, node A can say, I see based on this filter that you have these transactions, definitely have these transactions, so I don't need to include them. I know you have them. But I do need to indicate somehow that they were in the block. So it hashes the transactions and sends the hashes through instead. And that makes things very, very small. Instead of being 200, 300, 400 kilobytes for one transaction, it's like 32 bytes. That's 1,000 times smaller than a kilobyte. So it becomes super tiny compared to the actual transaction itself. So that allows the block to be very, very small. And when we look at the live network data, we'll see exactly how small it gets. But it also, let's take a look at this Bloom filter again. It goes through each transaction and says, do you have this one? Yes, yes, yes. These are all marked 1, so you probably do. Do you have this one? Yes, yes, yes. These are all marked 1, so you probably do. But let's say it comes to W here, and it says, do you have this one? Well, this is marked 1. This spot is marked 1 here, but here's a 0. So I know for sure you don't have transaction W. And this is really the key of how the Bloom filter helps the communication here. Because this cell is marked 0, the node that's sending the new block can tell that that transaction is not already on the receiving node. So it just includes it with the message. So back to the diagram here, Thinblock with missing transactions, it just simply includes any transaction that it knows for sure weren't indicated by the Bloom filter. So the Bloom filter can tell you for sure if certain transactions aren't included, but it can't tell you for sure if they might be there but are disguised by 1s. Let me explain what I mean, because I might have said that backwards. If this W were pointing to this one, and this one over here, then it actually would look like the first node had that W transaction, even though it didn't, because it would have a false positive. It would say, well, these are all 1s, so you probably hashed into those spots. But it would be wrong. So sometimes, and this happens very rarely, but sometimes the receiving node says, what? You didn't include that transaction? I needed that. So it actually has to do another round trip and send another message. I don't know if I can draw arrows here or not. You can't see my pointer at all. That's quite disappointing. I've been drawing on my slides, so I've just received a message saying they can't see it. Can you see? I'm changing my drawing indicator. Can you see this right here? I'm drawing an arrow. Here's one more message back that says, you didn't include this transaction, so I need it again. So I'll just write help, because I can't really write anything with lines. Help, I needed that transaction. My Bloom filter did have 1s there, but that wasn't the transaction I needed. It was just some other transactions that hashed into those same spots. And so then node A has to reply back again and say, okay, here you go. Here's an O. It's very difficult to write an O with lines. Okay, so this says, here's these last transactions that you were missing. And this doesn't happen that often. We'll get into exactly how often that happens. But this is a second round trip. If you count the round trips here, you would say, I'm curious, can you see my pointer? I can't switch pointers, never mind. So I'll have to indicate with lines from now on. That'll be interesting. This is the first round trip here. It's really half of a round trip because it's not all the way around. It's a one-way trip. And here's the second. So this now makes 1 round trip. So this is 1.5. Now usually that's enough, and that's the same quantity as the previous solution at the top. But then one more full round trip can be possible with those last 2. So it's possible to take 2.5 round trips, but it's almost always 1.5. So I hope that made sense. That's kind of the description of the Bloom filter and how that allows node A to exclude certain transactions, or really to hash them into a very, very small size instead of the full transaction. If you have questions about that, I can take that during the Q&A. We'll get into any details that you may have missed. So this is the architecture. Now let's talk about the impact that it has on the network. The first thing I want to focus on is how often the second round trip occurs. I have an interesting graph. This graph I did not create, but it is in the public domain, and it's very, very useful. This is the percentage of blocks that require the second round trip, basically saying I got this thin block and it did receive these hashes, but I needed this one other transaction. All I got was the hash. I needed a whole transaction. And this line up here, the green one, is 0. I needed 0 additional blocks. So this means right here, I'm drawing now. Right here means I did not need a second round trip. So you only need a second round trip 50 53% of the time. You need a second round trip 47% of the time because 53% was all of the transactions were already included. But this is without the Bloom filter. This is where the receiving node just says, I don't know what you have, so I'm just hashing everything and sending it over. That's the basic Thinblocks that Mike Hearn originally came up with. By adding the Bloom filter, that's able to be cut down to just 1.5%. So 98.5, if my math is correct, percent of the time, you only need that one round trip thanks to the Bloom filter. So that's why Xtreme Thinblocks is so much better than your standard Thinblocks. Because if there's any number here that's not 0, then you have to make that second round trip just to get those extra blocks, which takes more latency as you wait for that second round trip to take place, and it adds a little bit more bandwidth as you go send data back and forth again. So this just really highlights the importance of the Bloom filter, and that's what Xtreme Thinblocks is built around. So let's take a look at what impact that has on the size of the block. This is Thinblock versus a standard block. A standard block today is 1 megabyte here, and a Thinblock is 42 kilobytes. That is way smaller. That's like 4.2. So 0.042 times the full size. Okay, I think that math is correct. If it's not, you can do it yourself. It's way, way smaller, 24 times smaller. And this interesting diagram shows you the difference between the size of the Bloom filter, which is transmitted, and the size of the Thinblock here. This section here is you can see it's mostly Thinblock, but there's a fair amount of size that's committed toward the Bloom filter. But that's worthwhile in my opinion because that allows the second round trip to not have to take place. You can do it all in one communication. So with this smaller block, you would think it would transmit much more quickly. But first, let's dive into exactly the size of the Bloom filter versus the size of the block, because that changes based on how big the block is, and it changes based on the landscape of the transactions in the node's memory. So this is over a lot of different blocks. I think the bucket size is on the chart here. No, it's not. Oh, yes, it is. So n equals 6685. So this is a lot of blocks, 6,685 blocks were tested here. And once again, Andrea is going to be going into the methodology that they use to get this data. So the Bloom filter is sometimes small, but usually it falls right here in this range, and it almost never or really never is larger than this, which is like 22, 23 kilobytes, maybe 25. This is actually a log scale, so even though this is 20 kilobytes here, it runs all the way up to a megabyte on the same diagram. So it's quickly becomes larger. So these three horizontal bands are the Thinblock divided out between its block size and the Bloom filter. And this is network data that's transferred from node A to node B, and then from node B back to node A. So the Bloom filter is sent to the node saying, I need this block, here's what I have so far. And then the Thinblock, which is the middle section, says, okay, here's the Thinblock back. So this is communication in the other direction. And then the total bandwidth is the average is here 42 kilobytes per the previous slide. But you can see it differs a little bit. And so that's pretty good to take a look at because you want to know, especially this section over here on the right, where it ends up being quite a bit larger, because you don't want some blocks to be so big that even though the network usually works, every now and then the network goes down entirely. That's not okay. So you definitely want to run real-world testing to make sure that that's within the reasonable bands. So this is the size of the Thinblock. Let's take a look at how fast it is transmitted across the network, because that's really what matters. It's nice to save on bandwidth, but what's important also is for the nodes to be able to communicate quickly. So this is a pretty cool chart. As you can see, I mean, it just looks cool. Even if you don't know how to read it, it's already cool. The yellow is the Thinblock, and the gray is the competing standard block. And this is a box and whiskers chart here and here. If you don't know how to read those, I'll cover that briefly. The median value is the light green right there, that line in the middle, which is the middle result. And then the outsides of the block are the 25th percentile and the 3/4 percentile. So 25% of the data occurred outside here on this side, and 25% of the data occurred out here. As you can see, it becomes very scarce over on this side, and this is 1.5 times the interquartile, whatever it's called. Don't mind that part. So almost all of the data occurs in the rectangle there. That's the 25th to the 75th percentile. So that's the most important part to look at, except for the tail. And take a look at this tail here. I can't draw circles, otherwise I would just circle it, but I'll just underline it. This gray tail is blocks that are way too big, but it's kind of rare. So that's really important. As you saw in Andrew Stone's presentation, a few blocks are propagating really slowly. Well, a few blocks, this is that same data again. A few of the blocks are propagating really slowly, and this goes all the way out to 10 minutes. So this is that long tail of slow propagation. And take a look at the improvement that Thinblocks makes. On the yellow side, that tail is much, much thinner and much less significant, which means that Thinblocks are not experiencing those slow transmission times. And this is just the impact of Thinblocks. We saw in Andrew Stone's presentation just the impact of the, what was it called, expedited routing. I've forgotten his topic presentation already. It's slightly embarrassing. But each of these technologies taken by themselves already shrinks that tail. So together and with other improvements, we can really help block propagation on the Bitcoin network. So the median value here, which is the green, I consider that to be the most important because that's the midpoint of all blocks, is only half a second with Thinblocks, 1.5 with standard block propagation. Big difference. The mean value, which I don't think is as important, but it really emphasizes this long tail here, was 0.7 for Thinblocks, so still very nice and low. 8.4, that's because those very high or slow propagating blocks are pulling the mean up. Because really high outliers do that to a mean. And then the 95th percentile is also an interesting number, which is the very worst blocks, which is like the very slowest. The 95% of blocks were faster than this, and only 5% were even slower than this. And that's 10.9 seconds for the standard propagation versus 1.3. So you see huge improvements on the block propagation. And I feel confident I could say that the Thinblocks makes things over 5 times faster. Now, of course, it's different based on different metrics, whether you use the median or the mean, but the general takeaway is that it's a 5 times improvement, in my opinion. All right, so now we know how fast it is. Let's take a look at what this can do for the network. This is a little bit controversial, but I don't consider it to be controversial. I'm going to tell you why. This is the block size limit today, 1 megabyte, as you all know. We all grimace at that at the moment. I'm going to say that 4 megabytes is currently safe on the network with the slow propagation. And the reason for that, this is a tricky thing, is that the technology that's being rolled out on the network right now, segregated witness, actually has an attack surface of 4 megabytes. Because if an attacker creates transactions that are almost entirely witness data, then they can make basically 4 megabyte blocks. They can flood the network with 4 megabyte blocks if they're willing to throw away money and fees. So clearly, even our most conservative architects of the network are okay with an attack surface of 4 megabytes. Also, there have been studies. One study by Cornell University came out and said that the scaling impact of the network, the most important part is block propagation, which is what's being improved by Xtreme Thinblocks here, and that 4 megabytes is about the limit for safety. At 4 megabytes, they said, then we would lose about 10% of the nodes because they couldn't keep up with the larger block sizes, and that's like the threshold where it's okay to lose 10%, but beyond that, you're losing too many nodes due to putting out blocks that are too large. So that's the safe limit before. After Xtreme Thinblocks, with that 5 times transmission improvement, I argue that we can now use 20 megabyte blocks. Maybe that seems extreme, but last year we were actually looking at 20 megabytes with Bitcoin XT, and that's been reined in a little bit because, because there are certain people who wanted to stay at 1 specifically and wouldn't agree to anything, in my opinion, but everyone has their own opinion. So 1 megabyte block size versus 20 here, you can see the significant differences, the significant improvements we could have by 20 megabyte. We could have 60 transactions per second instead of 3. And this is really flies in the face of people who say Bitcoin can't scale, so it shouldn't. Some people say, let's not change the block size at all because we can't have a block size of 8 gigabytes. And so if you change it at all, we're going to have 8 gigabytes. So we just can't do that. Well, in my opinion, even a small improvement to scaling is an improvement to scaling. That can move the doomsday scenario where Bitcoin simply can't survive under its load out so that we have time to devise other solutions. And clearly we have other solutions coming forward. There are a lot of good ideas being presented at this conference that allow the network to scale more robustly. So it's important to take the small steps, in my opinion, so that we can then take a few more small steps and eventually travel down the path of better scaling. So 60 transactions per second would be a huge improvement. If you look at the graph of transactions over time, you'd see that that would give us a lot more time. In my opinion, several years before we'd have to scale again, so to speak. So that would be a big improvement. So for people who say that 60 is not enough because it's not Visa scale, it's still such a good improvement that it should still be done. So that's the impact of Xtreme Thinblocks. You guys have seen some other ideas at this conference that also improve scaling and allow for larger block sizes. When those are combined with Xtreme Thinblocks, then we see even better scaling improvements. So this is just one small thing that's improving the network, and you should keep that in mind. So let's talk about how you can get involved with Xtreme Thinblocks. The first obvious thing is to run a full node, and many of you are doing that. The Bitcoin Unlimited client is available now, and Thinblocks has been in this release since March of 2016. So for several months, people have been running this on the network. It's been working great. And version 0.12, you can download it at their website. I believe it's bitcoinunlimited.info. But who actually types URLs these days? You should just Google for Bitcoin Unlimited, and you'll find their website. So that's like the go-to for Xtreme Thinblocks because it was first designed there, and that's where it's been there for the longest. But Bitcoin XT just included this like 3 days ago at the time of this recording anyway, in version 0.11F of Bitcoin XT, so it's coming there as well. Clearly the XT folks say this is a great technology, we want to merge it. Bitcoin Classic doesn't have it yet, but it's on the roadmap for 2016, so it's very likely will be added soon. And Bitcoin Core has now jumped on the bandwagon as well. They're working on something called compact blocks, which many of you are familiar with, which in my opinion is so similar that it's basically the same thing. And I'm sure you're going to ask me about the differences, so we can get into that. So all of the major, I would consider these the 4 biggest Bitcoin clients. They're all getting on board with Thinblocks, with the way of transmitting a block without including all the transactions again. So clearly this is a good technology that's going to improve the network. And lastly, this forum address, bitco.in/forum, is kind of the home of Bitcoin Unlimited. Andrew mentioned the Slack channel at bitcoinunlimited.slack.com. You should definitely check that out. But they also talk, in a forum format here at these forums. So go take a look at those forums. There's all the unlimited proposals for changing the improvements and those kinds of things are discussed there on those forums. So go take a look. I'd recommend it. So this is the time where we would ask for questions. I'm going to go ahead and answer the first question now, even though nobody's asked it, because it's a very fair question. And that is, what in the world is the difference between compact blocks and Xtreme Thinblocks? And why don't they just use Xtreme Thinblocks? I mean, how is it better? So I'm going to go into a little bit of detail on how compact blocks is different. Let me jump back. This is the first Q&A. This is Q&A right now, and I'm answering my own question. Let's jump back to the slide that shows the second round trip required. You can see the Bloom filter really cuts down the number of times that you need this second round trip to transmit a block. Well, compact blocks, the big difference between that and Xtreme Thin is it takes away the Bloom filter. It says, you know what, this Bloom filter, let's get rid of it. Now it's different. We can name it our own thing. We can program it ourselves. Ha, 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 ha. Yeah, that's just one theory. Maybe they just think it's better without the Bloom filter. So that means that you need the second round trip a lot more often. There is one technique that they use, which is a good technique, which is to say, I know you're probably going to need these certain transactions. There's a heuristic, very simple heuristic that says you're probably going to need these transactions, so I'll include them anyway. And that is, when a new block comes in, it says, do I already have all of these transactions in my memory pool? And if there are any that aren't there already, it's likely that whoever I'm sending this block to won't have those same ones. So it doesn't hash those. It sends those in full, which makes the block slightly larger, but it allows the receiving node to much more likely be able to not need a second round trip. So that allows, from what I've seen claimed, I haven't seen studies on this, but what I've claimed is that the second round trip is needed in the order of 90+% of the times when it's not needed, so less than 10%, which is much better than this 47. I'm saying you need 47% of the time you need a second round trip. Well, with compact blocks, it's not 47%, it's somewhere less than 10%. Still not nearly as good as 1.5, but that's because they don't have the Bloom filter. So it's a different technique to do the same thing. Another difference between compact blocks and Xtreme Thin is that they salt their hashes, which is a fancy way of saying they shake salt on the potatoes. It's a way to prevent a extremely unlikely and useless attack vector, and it can also easily be added to Xtreme Thinblocks. So in my opinion, it's the same. In my opinion, Xtreme Thinblocks is compact blocks, because you can turn off the Bloom filter and bam, you've got compact blocks. Now, I should mention that there's actually two forms of compact blocks. There's the low bandwidth and the high bandwidth mode. And Xtreme Thinblocks is the low bandwidth mode. What I'm arguing is that they're like the same thing. The high bandwidth is a completely different technology. They just lumped it in there so that they could say it was different, but that's actually just, there's another technology called Xtreme expedited. It's called expedited routing, something like that. Basically the same idea as the high bandwidth. So compact blocks is really two technologies lumped into one. One of them is Xthin without the Bloom filter, and the second one is a different technology. So that's another way to say it's different, but in my opinion, it's pretty much the same. So let's answer questions from the chat now. First question is, what is the attack vector of knowing the transaction hashes? Yes, this is the reason that compact blocks salts their hashes, I believe. The attack vector, if you can inject all of the transactions into a node and say, okay, here's the ones that you're going to build the Bloom filter with, then the node builds an ugly Bloom filter. I think this is right. You know, I might be giving the wrong answer. I'm going to give you an answer, and if it's wrong, well, then at least I told you it might have been wrong. That should help. So if you can know the transaction hashes, is this giving my mind? Perhaps I don't know. I think it's that the Bloom filter is really large. I'm not 100% sure though. I would recommend asking that in the forums. The forum address is on the slide here. If you go in there and create a new thread and say, what is the attack vector of knowing the transaction hashes, then you'll get some geniuses answering that question for you. But I think it's because if you can determine the transaction hashes, then you'll get a really large Bloom filter. But I could be completely wrong, so we'll just leave it at that. Next question is, oh, cool. I don't see any other questions. That means I gave a perfect presentation because there's no confusion about what I spoke about. We'll give another moment for a few questions. By the way, the data that is in this slide, the size of the blocks and the transmission times of the blocks, that's a lot of sample data. It's thousands and thousands of blocks that were measured over the network. And that process that was used to collect that data will be in another talk in a couple of hours. Andrea is going to be talking about that in detail. So I actually didn't do that research work myself, but I was able to reap the benefit of it by using it in this talk. So I'm very thankful for that work, and it is very good work, but you should definitely stick around for that other talk to look at the methodology they used to gather that data. A question in the chat is, most people talk about spam, but they shy away from a definition of spam. Very good question. How would you define spam? I would define network spam on the Bitcoin network as a transaction whose purpose, the entire purpose of the creating of the transaction, is to clog up the network or slow down the network or to do something that relates to, I have to be very careful with my words here, because if I say, you know, to do something besides spending Bitcoin, then there's a lot of things that are included in that. But if I say something different, it means something different. So I would say that a transaction whose purpose is to fill the network, where the point of the transaction is to exist with a certain number of kilobytes in the block, and that's the whole purpose. If you're using a transaction to, say, indicate some asset, like a master coin or a counterparty token, where it doesn't move actual Bitcoin, but it does mean something to you. Maybe you've got some colored coin inside that transaction. I wouldn't consider that spam because you're actually using the Bitcoin network. And so you're going to pay a reasonable fee to get that to happen if there's fee pressure. But if you're creating transactions only to clog up blocks and make things more expensive for other people, that's definitely spam. So that's my definition. And we definitely, under that different definition, have seen spam in the network over the last year or so. If you take a look at the memory pools of nodes around the network, you see all these transactions that usually don't even get included in blocks, and they have very, very low fees. And it's often one address paying another address, paying another address. It's called a chain, where they're not doing anything except just paying themselves. And the point is to fill up the block to cause Bitcoin to be more difficult to use. That's definitely spam. So that's my definition. It has no purpose other than just filling the block. I've heard it argued that that there is no spam in the Bitcoin network, that if you pay the fee, then you're not spam because you're a paying customer. I disagree with that because I think it's wrong. It's a pretty good reason to disagree. We have a genius in the chat telling me the actual attack vector, so now you don't have to go to the forums and ask. So the question before was, what's the attack vector of knowing the transaction hashes with Xtreme Thinblocks? And the answer from the genius is to say that someone will try to inject 2 transactions in the pool with the same hash, so that Xthin is forced to execute a second round trip. That's a very good point. That was kind of something obvious that slipped my mind at the time. So let me talk a little bit about that. If you can inject 2 transactions into a node that hash to be the exact same hash, then of course they're going to fill out the Bloom filter in the exact same way. They're going to fall in the same slots of the Bloom filter. And so that means that the receiving node who gets that Bloom filter, it's impossible to know that there were 2 transactions filling up those slots, because it looks exactly like one. They're just all set to true. And so you don't know about both of them, so you won't include them both. And so then that requires a second round trip. So that's an attack that makes Xtreme Thinblocks require a second round trip every time. That's a guarantee. It's going to take a second round trip. I don't think that's a powerful attack, because all you're doing is slowing down propagation slightly, and miners don't depend on propagation of the entire block in order to mine. They already just mine off of the headers, which means they don't wait for the transactions. They just mine based on the block itself. And so that's going to continue to be true just because miners care about profits. So they will ignore the fact that the block is moving slower, and they'll just route it to themselves. The miners today use a fast relay network, a network that allows a centralized network to transmit the blocks to themselves quickly. And I don't think that's going away for a long time. So this technology is basically for the rest of the network to propagate blocks smoothly. I think it's going to be a long time before miners say that a decentralized solution is as good as just connecting to each other directly. One moment, please. Another question in the chat. How would you sell Xtreme Thinblocks to miners? What would be the benefit for them? Well, one reason it's better is that it's not worse. You see the improvements, and there aren't downsides. So, a good thing is better than not a good thing. I would say overall that miners don't benefit from Xtreme Thinblocks because they already use a centralized network to transmit blocks quickly. But that is not good for the network as a whole, because average people like you and me, when they run a node, they don't connect to that network. And so obviously we need a robust decentralized solution as well. So I think miners need to be a bit altruistic in order to say that the network as a whole is important and propagation is important for everyone, not just for me and for miners as a group. So I think that adding Xthin to their implementation is kind of an altruistic thing, a generous thing to say, I support the Bitcoin network being fast, smooth, and robust. So even though this isn't benefiting me personally, it benefits everybody, and that makes things indirectly better for me. Because as you know, miners mine Bitcoin. They don't mine dollars or euros or yen. So in the end, they need Bitcoin to have value in order for their business to even be profitable. And so things that are good for Bitcoin are good for miners. There's just no question about that. So even though it doesn't benefit miners specifically, it does benefit Bitcoin as a whole. So that's my argument for why miners should have it. Getting a couple of questions and comments at the same time, so let me take a moment to read through them. Is the statement that miners don't wait for transactions to start mining, assuming that they're doing some sort of optimized or headers first mining? If they wait for full validation, they must wait to get all the transactions they don't already have. Yes, you can actually see this happening on the network today. Sometimes you see miners mine an empty block, and every now and then we have a very angry Bitcoin citizen saying, look at that empty block, my transaction's not even confirmed and you mined an empty block, I'm so offended. Well, first of all, miners can mine whatever they want. If they solve a block, they don't have to put transactions in. But the reason we see these empty blocks is because miners haven't confirmed that all the transactions are valid. They haven't validated, that's the word, the transactions. And so they don't want to put out more transactions on top of those and then go back and find out that the earlier ones weren't valid. So they're not going to shut down their miners just to make sure the transactions are valid. They'll leave their miners running, and if they find a block, then they'll simply mine it empty just to be sure that it's not going to be invalid. And that's why we see these empty blocks, and we're going to continue to see them. I don't think any time in the future we're going to start seeing every block with transactions, because if you find 2 blocks 1 second apart, the second block, it's simply not safe to include transactions in case the first one turned out to be invalid. So they've mined an empty block just to be sure that it's not going to end up being invalid. And that kind of ties into why miners don't need the block contents to propagate quickly. All they need is the block headers to confirm that it has the proper proof of work. So that's that. Another question, what about spam from flooding total connections on nodes? We saw recently spam flooding total connections on nodes. I'm actually not aware of that attack. Last year, we definitely saw spam flooding transactions where memory pools jumped up to the hundreds of megabytes. And that was actually a demonstration of how robust the Bitcoin network is. Some people say it can't scale because of all these transactions traveling through a peer-to-peer system would be very inefficient. But we saw transactions per second, very, very high, 100 or 200 transactions per second, even though we can only process 3 per second in an actual block. So we saw the peer-to-peer network very robust at that time. But this question is about connecting to a single node with a lot of connections and kind of taking it down, saying, look, I'm 100 people and I'd like to talk with you right now. And that node becomes overwhelmed and is attacked. Unfortunately, I'm not aware of that attack, so I can't comment on it. Comment, one more question. A comment that says the empty blocks are a natural mechanism to limit the transaction rate. I disagree with that. I think empty blocks would be better if they weren't around. It'd be better if every block contained the transactions that it could, so that Bitcoin transactions would process more quickly and smoothly. But empty blocks are simply a side effect of not being able to validate transactions instantly. So during that validation, you might mine an empty block. So it's a bad thing in my opinion, but it's inevitable under the current architecture. One more comment. Reflecting back to the question about how I would sell Xfin to miners, I said that it would have to be kind of altruistic to add Xtreme Thinblocks because you're already communicating quickly with miners. This comment is just mentioning that expedited routing, I think it's called, that's being worked on by Andrew Stone right now, is really a miner-specific technology. So that's for the miners, and Xtreme Thinblocks is for the rest of the peer-to-peer network. So now you kind of do need different technology between the miners and the rest of the network at this point. Because Bitcoin has become so large and because miners have grouped together into mining pools, they kind of have different needs. The miners need to receive the proof of work headers very quickly so that they can mine on the next block, but the rest of the network doesn't need that. The rest of the network needs to see the transactions as they come in and the transactions are confirmed. So it makes sense that different technologies would be best for those different groups, or at least most useful for different groups. And that technology is called expedited routing. I'm not going to get into the details on that too much, but it's basically allowing the blocks to be transmitted between miners quickly by flooding them. Instead of saying, here's one, would you like it? And then waiting for the answer. Oh, you would like it. Okay, here you go. And I'm sending it over to you. The expedited routing just says, I got one, here you go. And it just floods the network with it. So it uses more bandwidth, but it's very, very fast. And so that's important for miners because they care about time more than anything else. Hey, they care about me because Chronos means time. Very good. Looks like that's all the questions. So thank you so much for the honor of presenting on Xtreme Thinblocks. And I hope you're enjoying the conference.